Good morning, everyone. This is course P3321, Molecular Physics. We are going to start with chapter 2, named Rotational Spectra. We are going to study in this chapter pure rotational spectra of diatomic molecules. Let's take a look on the content of chapter 2. We will start with some experimental observations that are related to the rotational energy or rotational energy levels of molecules. Then we are going to deal with diatomic molecules as rigid objects. We will start with a classical approach, try to find their moment of inertia, and try to figure out their rotational energy in order to take an idea about what's going on. Then we will move to the quantum approach and try to calculate the energy of rotation of diatomic molecules using quantum mechanics. Then we will see how these rotational energy levels degenerate. After that, we will define two terms, the rotational constant and the spectral term. They are important in dealing with spectra of diatomic molecules for pure rotational cases. After that, we will talk about rotational selection rules. What are the rules that must be followed for a transition to be allowed from a certain rotational energy level to another? These rules allow a certain appearance of rotational spectra or a certain form of rotational spectra that we are going to understand and deal with. Then we are going to talk about level populations, how the energy levels are populated, which one of them has more population of molecules than other levels. And for sure, we are going here to deal with Boltzmann distribution. After that, we are going to deal with a real rotor, because all in the previous parts we have dealt with a rigid rotor, where we have considered our molecule to be rigid. Now we are going to consider it here a real rotor and try to calculate the centrifugal distortion, which affects for sure the shape of the spectrum and the energy, the separation of the energy levels or rotational energy levels. At last, a quick explanation for rotational Raman spectroscopy, and at the end there are some exercises. Each one of these topics will be explained in details throughout this chapter, so follow up with me. As a first step, let's take a look on these experimental data for HCl molecule in the gaseous phase for wave numbers of the absorption spectrum. So what is the absorption spectrum of a molecule? The absorption spectrum is the fraction of incident radiation absorbed by the material over a range of frequencies of electromagnetic radiation. يعني نحن بناخد هيدي الموليكول اللي هي HCl. أكيد نحن بحالتنا in the gaseous phase. It is radiated by a group of frequencies or a range of frequencies, and then we check what frequencies are absorbed by this molecule and at what intensity. So this will give us the absorption spectrum. Let's take a look about the results for HCl molecule. So we have seen that there is absorption at the wave number. The unit is centimeter minus 1. The first one is 83.03, 104.10, 124.3, etc. So we can see that the values of the wave numbers are not continuous and they are discrete. So we think about quantized energy levels for this molecule. Not only that, but there's something quite interesting. If we try to calculate delta nu bar, or the difference in the wave numbers of two successive lines, for example, the difference between the first and the second, subtract 104.10 minus 83.03, you will get this number. So then subtract 124.3 by 104.10, you will get this number. So this difference between two successive wave numbers of two successive lines is approximately constant. So it's 21.07, 20.20, 20.73, 20.48, etc. So it's approximately constant. As an average, it's approximately equal to 20.51 centimeter minus 1. So one may assume that we can calculate these values or the values of the wave numbers for HCl molecule using this formula, which is A times M, and M is an integer. Let's check if this is true. So we have taken this A, which is a constant, equal to 20.51, and multiply this constant by 4 to get a value, mu bar, equal to 82.72, which is very, very close to the experimental value. Again, multiply 20.51 with 5, you will get a value very close to the experimental value. So we can assume that this formula or this empirical formula is somehow okay to deal with, but we still don't know the origin of this formula. So later we will demonstrate that this spectrum can be explained as the conversion of absorbed electromagnetic energy into rotational energy. So we will see that the energy absorbed here is related to the rotational energy of the molecule, and we will see how. The absorption is not a continuous process as evidenced by the quantized energy levels observed in the absorption spectrum. So we have seen that the energy levels are not continuous because we have seen discrete absorptions at different positions. So we expect that our energy levels are quantized. Just to make things clear, the subtraction of these two levels or these two wave numbers gave this, then subtraction of these two gave this, and the subtraction of these two gave this, then these two gave this, and so on. So this is the way they were calculated. The last one is based on an unvalid information here. This is a typical absorption spectrometer. So this is a source that emits a range of frequencies of electromagnetic radiation that passes through a reference cell and a sample. Here they are reflected by two mirrors here, and it passes through a sample and through a reference, and then they are collected to reach the detector so that the relative absorption can be determined. So in this case, we can determine the pure rotational spectrum of only the sample without any external interventions. This is done for sure through a comparison between the ray coming from the sample and the ray coming from the reference. Up till now, we have seen experimental evidence of what will be proven later to be related to rotational energy levels. So let's start with the classical approach of a rigid rotor. In this approach, we are going to deal with rotation classically. The molecule is considered to be rigid. The distance between atoms or nuclei is considered to be constant all the time, and the molecule is rotating about an axis passing through its center of mass. To study rotation of this molecule about a certain axis of rotation, we have to find its moment of inertia, because to find the energy, we have to pass through the moment of inertia before. The energy is related to the distribution of mass around the axis of rotation. What is the moment of inertia of a molecule? So, similar to the moment of inertia of any system, the moment of inertia of a molecule is defined by summation of I mi square xi square. This is true for any molecule, not only diatomic molecule. So if we have a rotational axis passing through the center of mass of the molecule, then we multiply the mass of each atom of the molecule by square of the distance, the shortest distance or the perpendicular distance to the axis of rotation. So xi is the perpendicular distance of the atom I from the axis of rotation. And then we do a summation over all the atoms constituting the molecule. Normally, three perpendicular axes can pass through the center of mass of the molecule in order to describe totally the rotation of a molecule. So in general, the rotational properties of any molecule can be expressed in terms of moments of inertia above three perpendicular axes set in the molecule. So as you can see here, there are three perpendicular axes which describe the whole rotation of the molecule. I said earlier that we are interested in this course in diatomic molecules only. So let's try to calculate the moment of inertia of a diatomic molecule, as you can see here, about an axis passing through the center of mass of the molecule and perpendicular to the internuclear axis. So this is our axis of rotation, and this is the internuclear axis. No rotation is considered along the internuclear axis because simply the moment of inertia around this axis is zero. Remember that I equals summation of mixi squared, and because the distance of m1 or the first atom from the internucleus axis is zero, and similarly atom 2 has a zero distance from the internuclear axis, the total moment of inertia of the molecule around this axis or the internuclear axis will be zero. So only possible rotation will be around an axis perpendicular to the internuclear distance. Now we have understood why we are going to choose our axis of rotation like this, perpendicular to the internuclear axis and not along the internuclear axis. Now, why does our perpendicular axis of rotation pass through the center of mass or must pass through the center of mass? In classical mechanics, we know that if we have an isolated system or a system where no external forces are acting on it, summary moments is zero, or summary forces is equal to zero, it must be rotating around its center of mass. Otherwise, it will be accelerating or decelerating. Now, after defining our axis of rotation, which passes through the center of mass of our diatomic molecule, let's start calculating the moment of inertia about this axis. So I is equal to m1x1 squared plus m2x2 squared, where m1 is the mass of the first atom or nucleus. It's the same because the mass of the whole atom is concentrated in the nucleus. x1 is the distance from the center of atom 1 or nucleus 1 to the center of mass of the molecule. m2 is the mass of the second atom or second nucleus. x2 is the distance from the center of the second nucleus or atom to the center of mass of the molecule. Now let's try to calculate x1 and x2. Let r be the distance between the two atoms forming the molecule. So r is the internuclear distance. x1 is the distance of the first atom and x2 is the distance of the second atom from the axis of rotation. So first, because x1 and x2 are the distances from the center of mass, we have m1x1 equals m2x2. Where does this formula come? I bet you still remember the formulas of at the center of mass of a system. So let's just remind you. So let's draw an x-axis to make things simpler. And this is O, the origin of the x-axis. Let's place G, the center of mass of the molecule, at O. So let's take here M1, the first atom, and M2, the second atom. Remember that the distances are x1 and x2. These are the distances, they are positives. So at an abscissa, the abscissa of M1 will be minus x, and the abscissa of M2 will be x2. So let's write the formula for the center of mass. I'll write it here. So you remember that xg will be equal to M1, the abscissa of the first particle or the first atom of the molecule, which is minus x1, Why? Because the abscissa must be negative and x1 is defined to be a positive distance, plus m2 x2 over m1 plus m2. Because we have already chosen g to be at the origin of the x-axis, xg will be equal to 0. Okay, so we remain with minus m1 x1 plus m2 x2 is equal to 0, which leads to this formula. So this is the way we arrive to this formula. Once we have equilibrium between two parts, then m1 x1 must be equal to m2 x2. We are going to try to find x1 and x2 in terms of r, the internuclear distance. So here we will substitute x2 with r minus 1, because as you can see, x1 plus x2 is equal to r. So we replaced x2 with r minus x. So we arrive to an equation that contains only x1. Distribute, arrange the equation, you will get x1 equals m2 over m1 plus m2r. So we arrive to an equation that shows x1 as function of m1, m2, and r, things that describe a molecule. Similarly, we are going to use the same formula. So this is the same formula as above, but here we are going to replace x1 with r minus x2. So now we arrive to a formula. Now we arrive to an equation that only contains x2. As you can see, m1 r minus x2 equals m2 x2. So it only contains x2. Distribute, arrange x2 to one side, you will get x2 equals m1 over m1 plus m2r. Again, x2 is a function of m1, m2, and r, the internuclear distance. Now we can find I. I is equal to m1. We substitute x1 for its value, m2 over m1 plus m2r squared, plus m2, m1 plus m2r squared. So we just distribute the squares, we will get m1 m2 squared over, I'll write it here, so it's m1 plus m2 all over it squared, plus m2, this is m1 squared over m1 plus m2 squared r squared. Okay, which is equal, we can take as common, we can take r squared m1 m2, this is squared with the brackets, m1 plus m2 squared. So let's take a common, we will get m1 m2 r squared over m1 plus m2 all squared. There remains, from the first one there remains m2, and from the second one there remains m1. So you can see that this bracket cancels out and we are left with m1 m2 over m1 plus m2 r squared. This is the final answer. So let's erase a little bit to be able to see what's below. Let me erase everything. Okay, if we take a look on this formula, I equals m1 m2 over m1 plus m2 r squared, it's very close to the moment of inertia that corresponds to a single particle if this particle was rotating about an axis with a mass. This is the mass of the particle and r is the distance from the axis of rotation. In other words, the rotation of a diatomic molecules whose atoms have masses m1 and m2 respectively and an internuclear distance r has a moment of inertia similar to a single particle with mass mu called the reduced mass and a distance r from the axis of rotation. So this is the distance r of the axis from the axis of rotation. يعني إذا بدكم الروتيشن تاعت الداياتوميك molecule هي بتشبه الروتيشن ل single particle عندها mass M1 M2 على M1 plus M2 نحن بنسميه reduced mass، وهيدي البارتيكل بعيدة مسافة R اللي هي internuclear distance عن الأكسس of rotation. So بدون ما نعالج بعدين المواضيع ما ناخد اثنين particles ونحكي عنهم، we can just assume a single particle rotating about an axis with a distance R وبيمشي الحال. We can do that. It's okay, it's fine. وأكيد هيدي البارتيكل رح يكون عندها mass mu و reduced mass of the atom. إذا بدكن هيدا رسم تقريبي اللي أنا حكيته. هون عندي diatomic molecule. Here we have a diatomic molecule rotating about an axis perpendicular to the internuclear distance passing through the center of mass with moment of inertia I equals m1 m2 over m1 plus m2 r squared. The similar is explained by a single particle. This is a single particle having a mass mu and away from the axis of rotation a distance r, similar to the internuclear distance. So r here is the internuclear distance. So here the same, I is equal to mu r squared. So both systems are equivalent. So if we are going to calculate, for example, the energy of a diatomic molecule, we can make benefit of this equivalent mechanical model. Let's read these notes. So if M1 is equal to M2, we have a homonuclear molecule. That means a molecule with similar atoms. Then mu will be equal to M1 over 2. So let me just write it. So mu is equal to M1 M2 over M1 plus M2, which is equal, so let's call it M, so it's M squared over 2M, which is equal to M over 2. Now if M1 is much smaller than M2, so if M1 is much smaller, يعني we have a very light atom and a heavy atom, so in this case M1 is much smaller than M2 and we are left with M1 M2 over M2. As you can see, so M1 is neglected in this case. So M2 with M2 cancelled, we are left with M1. So we can say that, or we can see that mu, the reduced mass, is between M1 over 2 and M1, which is M1 is the lightest atom. So here M1 is the lightest atom، يعني هي الأتوم الأخف. هون بكل الأحوال M1 هي كانت نفس الوزن. So بكل الأحوال, in all the cases, mu is between M1 over 2 and M1, where M1 is the lightest atom. بأسوأ الأحوال بيكونوا قد بعض. M1 equals M2. So in this case, mu will be equal to M1 over 2. So M1 and M2, or the choice of the masses, affects mu. وكمان it affects the axis of rotation. It affects the position of the center of gravity, as you all know. Now let's calculate the rotational energy of a diatomic molecule classically. We all know that this rotational energy is kinetic. It's not potential, it's purely kinetic. So the formula is easy, we all know it. The kinetic energy of rotation around a certain axis of rotation, let's call it A, it's equal to half I omega squared. So as you can see, the energy about an axis A is equal to half IA omega A squared, where omega A is the angular velocity. It has a unit of radians per second about the axis of rotation, and IA is the moment of inertia about the same axis. So if we are talking about a body free to rotate about any axis in space, for sure we have three axes, perpendicular axes, let's call them A, B, C. So the total rotational energy will be of this form. We are concerned about a diatomic molecule. For a diatomic molecule, we have said that there is no rotation around the internuclear axis. The only rotation is about an axis perpendicular to the line of atoms. So in reality, we have two axes perpendicular to the lines of atom and one along the lines of atom. So 1 will be 0 and we are left with 2. Along these two, so let me draw it just for you to understand it. So this is our case, this is our atom. Okay, so this is X, Y, Z, just to understand it a little bit. So you can see here the internuclear distance is along the y-axis. So there is no rotation around y. There is only rotation about the directions that are perpendicular to the internuclear distance. So there's a rotation around z and there's a rotation about x-axis. The moments of inertia about z-axis and x-axis are equal because the distribution of mass is the same. You can see it clearly. So I have replaced IA by simply I and IB by I. So you are left with omega A squared plus omega B squared, which is the rotation about the A axis and the B axis. We end up with the total angular velocity, omega squared. This is just to say that it is possible that a molecule is not rotating about x or z direction, but around an axis perpendicular to the internuclear distance in between x and z. At the end, you may use directly E equals half I omega squared, where omega is the angular frequency about this axis of rotation. There is another way to calculate the rotational energy of a diatomic molecule. Because we have 2-point particles M1 and M2 rotating about an axis of rotation, so we can calculate their energy as half M1 V1 squared plus half M2 V2 squared. You can work a little bit with this, substitute V1 with omega x1 and V2 with omega x2, and then you will arrive to the formula half I omega squared. Anyway, I'm going to use the equivalent mechanical model, which constitutes of using a particle at a distance r and of mass mu, which is the reduced mass of the molecule. So we can say that this diatomic molecule is similar to a single particle that has a mass mu and velocity v. So its energy will be half mu v squared. Because it's away from the axis of rotation in distance r, so v is equal to r omega. So replacing this, we will arrive to, this will give us I, will arrive to half I omega squared, similar as before. It can be seen from the equation above that for a diatomic molecule in rotation obeying the classical mechanics, its rotational energy is only dependent on the moment of inertia of the system and its molecular velocity. So energy depends on I and omega. No restriction, furthermore, is placed on the angular velocity with which the molecule can rotate. So up till now, there is no restrictions. The molecule can rotate with any energy, with any angular frequency. There are no rules, no quantization. This classical treatment does not allow to interpret and explain the experimental results that showed that only specific energetic states were only allowed for that rotating molecule. Because the classical model is unable to interpret that, we are going to move to the quantum model. According to classical mechanics, E equals half I omega squared. We have already seen that. We can replace I with J over omega. So I equals J over omega, where J is the classical angular momentum and omega is the classical angular frequency. So we have this form. Energy equals J squared over 2I. Remember that J here is the classical angular momentum. You must have already seen when solving the hydrogen atom that square the magnitude of angular momentum is replaced by j plus 1 h bar squared, where j here is a quantum number that goes from 0, 1, 2, it's a positive integer. It can be 0 also. So here, this is the classical angular momentum. Here, J is a quantum number. And this one represents the square of the angular momentum in quantum mechanics. So h bar squared for sure is equal to h over 2 pi, where h is Planck's constant. You all know this information. So if we replace here j squared, here we're going to replace j squared with a j plus 1 with a j quantum number, h bar squared, we're going to see that our energy or our rotational energy is quantized. It's a function of a quantum number j that goes 0, 1, 2, etc. This energy depends on the quantum number j and on the moment of inertia of the molecule. But is this true? To know that, we must solve the Schrödinger equation for rotational energy. So let's do that together. Let's solve the rigid rotor Schrödinger equation. I will do it rapidly. It's not required, but it's good just to see it, to know that we'll arrive to the same value of energy. So a complete quantum mechanical description, the wave functions and the energies of allowed states can be obtained by solving the Schrödinger equation for a rotating linear system. So because it is a rigid rotor, the distance between the atoms is constant, only two variables theta and phi are left to deal with. So the rigid rotor wave function, psi, is only a function of theta and phi in spherical coordinates, and there is no r. So let's assume we can divide it to two functions. One is a function of theta and the other function of phi. And try to substitute our wave function in the Schrödinger equation using spherical coordinates. So the Schrödinger equation is given by h psi equals e psi. H is the Hamiltonian, psi is the wave function, and E is the corresponding energy. So because our molecule is found in no potential, so there is no potential, only the part of the Hamiltonian that is left is minus h bar square over 2 mu nabla square. Mu is used here to represent the reduced mass of a molecule as if we have a single particle of mass mu. Now let's complete substitution. We are going to substitute nabla square for its value in spherical coordinates. So here it is. This is the value of nabla square in spherical coordinates. And we have replaced psi with theta phi, and similarly in the other side. Now we are going to replace mu r squared with I, which is the moment of inertia, classical moment of inertia of the molecule. And we are going to get rid of r because r is constant. Our functions not depend on r, and there is no derivative with respect to r. We remain with the parts that contain theta and phi. Now we will try to rearrange the equation. We're going to divide by theta phi, and we're going to multiply by sine squared, multiply all the equation by sine squared, theta, divide by theta of theta and phi of phi. We're going to multiply by minus 2i over h bar squared to get rid of this constant here. So let's do that, and we will arrive to this form. So as you can see, we arrive to this form. Now let's call 2ie over h bar square as lambda. Lambda is an arbitrary parameter. It has nothing to do with the wavelength of light. It's just a parameter to tell that it is the multiplication of different constants together. Substitute lambda here and rearrange the equation, grouping theta and functions of theta to one side and phi to the other side. We can see that we are able to separate variables, each one to one side. The only way two different functions of independent variables can be equal for all values of the variable if both functions are equal to a constant. So these two functions are equal only if both of them are equal to the same constant. Let us call this constant m square. Why did we choose m square? Because m will have a physical meaning later. So if this equation is equal to m square, arrange it, you will get this form. You can see that the partial derivative is replaced by a normal derivative d because our equation is an equation of one variable and we don't need the partial derivative anymore. The second equation is also equal to m squared, so arranging it, you will get this form. Solving this equation is quite easy. It will have an exponential solution. The phi equation has the solution phi equals n e plus or minus I m phi, where n is the normalization constant, phi is the variable, and m corresponds to m squared, which is the constant already chosen. Values for m cannot be arbitrary due to the cyclic boundary condition. We know that if the molecule undergoes a complete rotation, its wave function must return back to its initial value. So if we replace phi by phi plus 2, the wave function must return to its value. We will get n e plus or minus I m phi plus 2 pi, which is equal to n e plus or minus I m phi e I plus or minus for sure m times 2 pi. So this function is equal to its initial value. Its initial value was n e plus or minus I m phi. This is the initial value. Only if this part here is equal to 1. And this happens if m is an integer. It can be a positive integer, a negative integer, or even 0. So there is a condition on m. M is not an arbitrary number. It is an integer. Theta equation is more complicated. Solutions of theta equation are related to associated Legendre functions. This course is not going to deal with the solution of the Schrödinger equation in details. You are only interested in the energy levels or rotational energy levels of a diatomic molecule, and we're going to understand their spectra and not more than that. So back to our theta equation. Here's our theta equation. This equation has only solution if this lambda is equal to j plus 1, where j is a quantum number, a positive quantum number, such that j is greater than absolute m, which means that j or m, write it like this, is between minus j and j. So there's a relation between j and m. And up till now, we have two quantum numbers that control a rotational level of a molecule, m and j. M is also called mj specific. So each pair of values for the quantum numbers j and m identifies a rotational state and the wave function. So how to deduce the energy? Back to the definition of lambda. Lambda equals 2IE over h bar squared. So the energy is equal to lambda h bar squared over 2I, and lambda is simply equal to j plus 1 h bar squared over 2I. We have seen that the rotational wave function is defined by two quantum numbers, j and m, while the rotational energy is only dependent of one quantum number, j. That means we have two j plus 1 wave functions corresponding to the same energy. This is called the degeneracy of a rotational level. The degeneracy for a certain energy level is given by 2j plus 1. Why 2j plus 1? We have said earlier that for a certain j, there are or values of m range from minus j till j. So as you can see, for j, we have 2j plus 1 values. So j values to this side, j values to the second side, and one value in the middle. Adding all of them up will be 2j plus 1 values for m. So that means for each j, we have 2j plus 1 values of m. So we have 2j plus 1 wave functions having the same energy because the energy does not depend on m, it only depends on j. Let's take an example. If j is equal to 1, m can be equal to minus 1 or 0 or 1. So there are three possible states which are j equals 1, m equals minus 1, j equals 1, m equals 0, j equals 1, m equals 1. These states are three different states, but they have the same energy. So we say that we have a degeneracy equal to 3, which means that j, which is equal to 2j, in our case is 1, plus 1 is equal to 3. Three states having the same energy. The degeneracy associated with the quantum number mj is partially removed when an electric field is applied to a polar molecule. The splitting of states by an electric field is called Stark effect. The energy shift depends on the permanent electric dipole moment. This is just given for you as general information. So if we have a polar molecule means that we have a molecule where positive charges or the center of positive charges is to one side and the center of negative charges to the other side. So we have some sort of a dipole. This is a polar molecule. If we have a polar molecule and we have a permanent electric dipole moment, mu, so this is the permanent electric dipole moment, it's equal to Q times D. Remember the electric dipole moment, mu, if we have two charges, one is plus Q and the other is minus Q separated by a distance D, then the electric dipole moment is equal to QD. So if we have a molecule with a permanent electric dipole moment and we apply an external electric field, we are able to separate the energy levels that have the same J but different mj, and we are able to observe them. So this is Stark effect as is. So now if we assume that the electric field is oriented along the z-axis, we can represent the motion of the molecule as a combination of movements. This is the z-axis where we assume that the electric field is oriented. So this is the electric field. This J represents the angular momentum of the molecule. The molecule rotates around its axis represented by J. You can see that all these molecules have the same J, but they have different orientations in space, and this orientation is represented by mj. You can see that mj is the projection of a J along the z-axis. Meanwhile, the molecule is rotating around the z-axis with a motion called the precisional motion. So it's rotating like this. It's similar to a taupe. يعني الموليكول عم تبرم حول axis والaxis هو بحد ذاته عم يبرم حول z-axis. So, in the presence of an electric field along z-axis, the molecule rotates around its axis, and this axis rotates around the z-axis in a motion called precisional motion. So كتير بيشبه حركة البلبل. البلبل بيبرم حول الأكسس تاعوله، والأكسس تاعول البلبل بيبرم حول أكسس تاني. Now let's define the rotational constant and the spectral term. We have found the energy of the rotational level is equal to J plus 1 H bar squared over. Now let's define these two terms, rotational constant and spectral term, that are used to understand the spectra or rotational spectra of a molecule. The energy is normally expressed in terms of the spectroscopic rotational constant of the molecule, simply the rotational constant of the molecule. The definition of the rotational constant as a wave number is convenient. So the rotational constant is giving the symbol B bar or B tilde. This is a wave number. It has a unit of centimeter minus 1 and it's equal to h bar over 4 pi c times I, where I is the moment of inertia of the molecule and c is the speed of light in vacuum. Sometimes the rotational constant is defined as a frequency instead of a wave number. So it's written B equals h bar over 4 pi I. We have already seen that V equals C V bar. So for sure B will be equal to C V bar. Now we have seen that the expression of the energy is equal to J plus 1 h bar squared over 2I. We can replace h bar over I with, so from here, h bar over I, it's equal to 4 pi cb. So we will get equals j plus 1, and h bar remains, it's 4 pi cb divided by 2. So 2 with 2 is cancelled, so 2 pi h bar is simply h, so we arrive to j plus 1 h c b. And this is the form of the energy. It's either written this way or simply cb bar is equal to b. It's hb j plus 1. We are going to use this form because we care more about the wave numbers. Let's now define the spectral term. Instead of defining the energy, it's good to define the spectral term. The spectral term is similar to the energy, but instead of using an energy, we're going to use a wave number. So the energy of a rotational state is normally reported as the rotational term or spectral term, a wave number expressed in centimeter minus 1. How to move from energy to a wave number? We divide by hc. So dividing by hc, we will arrive to the spectral term f of j equals b j plus 1. Now before moving to the next slide, let's take a look on this diagram here. You can see if we substitute for j equals 0, we will get the first one, the first wave number, f of 0 is equal to 0, 0b. And then for f equals 1, we will get 1 plus 1, it will be 2b. And then for j equals 2, we will get 6b, and so on. These small levels here express the degeneracy of the level. This one, each one has a degeneracy 2j plus 1. So the first one has a degeneracy 1, the second one 3, the third one has 5, etc. What concerns the difference between energy levels, so these two has a difference 2b, the second is 4b, the third is 6b, okay, and so on. So the separation of adjacent levels can be found by subtracting fj plus 1 minus fj. So if fj is equal to j plus 1 b, or bj plus 1, so fj plus 1 is equal to b j plus 1, I have to add to j1, j plus 2. So we will arrive to this form for fj plus 1 and this for fj. Subtracting them, we will get 2bj plus 1. So again, if j is equal to 0, we will get 2b. So this is the first difference between J0 and J1. So if J is equal to 1, if J is equal to 1, we substitute. So this is the difference between 1 and 2. This will give me 2b, 1 plus 1, this will give me 4b. So the second difference is 4b. And if J is equal to 2, I'm finding the difference between the levels 2 and 3, because this is a J plus 1. So it will be 6b, similar to the data already found in the previous slide. What happens when the quantum number J increases? When J increases, the separation between the levels increases, delta F increases, delta F depends on J, so that separation between the levels will increase. This is the first thing that will happen. The angular momentum, J, will increase. We know that J squared is equal to, this is the angular momentum, is replaced by the quantum number Jj plus 1 h bar squared. So as J increases, the angular momentum will increase. So if the angular momentum is increasing, the rotational speed will increase because J is equal to I omega classically. So if the angular momentum is increasing, the rotational speed must be increasing as well. So for higher energy levels, the rotation will increase of the molecule, its angular momentum will increase, and the separation of the levels will increase also. So we have seen that the quantum number J determines the value of the angular momentum. And when the value of the quantum number J increases, that means that the angular velocity of rotation of the molecule will also increase. We have already seen that in the previous slide. Now, what is the significance of the quantity B? B is related to the moment of inertia of the molecule. So B equals h bar over 4 pi ci. H bar is a constant, c is a constant, 4 pi is a constant. It only depends on I, on the moment of inertia. Typical values of B for small molecules are in the range of 0.1, 10 cm minus 1. So rotational transitions lie in the microwave region of the spectrum. From this table, you can note that the values of B for different diatomic molecules is between 0.1 and 10 cm minus 1. So these are the values of B bar. And this is the internuclear distance. And you can also note that from this table that if we replace an atom by its isotope, here we replace hydrogen by deuterium, so the internuclear distance has barely changed. So replacing an atom by its isotope has negligible effect on the internuclear distance. So here it's the same. If we replace hydrogen by deuterium, we can see that the internuclear distance approximately remains the same. So B changes. Why does B change? Because simply I changes, the mass changes. So I changes, we have a different B. So B depends on I, on the distribution of mass or on the moment of inertia of the